Okay, maybe we will start. So today we'll discuss about Brilliant John. So, so what is a Brilliant John? Before understanding that, uh, is a valid question to ask: what is the primitive cell in reciprocal lattice? We have talked a lot about primitive cell in real space, in real lattice. Now, what is the primitive cell in a reciprocal lattice? The answer to this question is it is the Wigner seed cell. It is the Wigner seed cell in the reciprocal lattice that is called the first Brillouin zone. It is the Wigner seed cell in the reciprocal lattice that is called the first Brillouin zone. How was the uh, Wigner seed cell constructed? Let me remind. Hmm. So let me start. So the Wigner seed cell. So if we had like points somewhat like this. Okay. Then what we try, let's take for example this point of interest. We take the perpendicular bisector here. And then similarly between this point and this point, we try to get the perpendicular bisector. This point and this point, we try to get the perpendicular bisector. Hmm. This point and this point, we try to get the perpendicular bisector. This point and this point, we try to get the perpendicular bisector. So if we try to see what the region bounded by all perpendicular bisectors, then that is somewhat like this region. Hmm. So this is basically the region. Hmm. So that region was called the Wigner-Sich cell. Now the this is also a primitive cell. This is also a primitive cell. What is the definition of primitive cell? That there is to be only one lattice point per primitive cell, per cell. So in a primitive cell, there is only one lattice point. One lattice point per cell. Okay. So here the way we construct that method by perpendicular bisectors are called Wigner-Sich cell. Now in a reciprocal lattice, what exactly it is telling? Let me come to the yeah. It is the Wigner-Sich cell. It is the Wigner-Sich cell in the reciprocal lattice that is called the first Brillouin zone. So, what is first Brillouin zone? It is the Wigner-Sich cell in reciprocal lattice. The concept of Brillouin zone is very special importance in understanding the electronic structure of solid and band theory. So, when we discuss about band theory, then this first Brillouin zone is very much important. The concept is the dynamics of electron in the first Brillouin zone will almost be similar in other Brillouin zones. So it is by method of or by periodicity, we can simply generalize that whatever dynamics is happening for the electron in the first Brillouin zone is valid in other Brillouin zones. So it is not necessary to study other Brillouin zones. It is important to study the dynamics of electron only in the first Brillouin zone. That will be more clear when we study band theory of solids and Crony-Penny model, etc., in the subsequent chapters. So the first Brillouin zone is the smallest volume. First Brillouin zone is the smallest volume. It is the volume obtained by planes that are perpendicular bisectors of the reciprocal lattice vectors. It is the volume obtained by the planes that are perpendicular bisectors of the reciprocal lattice vector. Okay. In the following, this is illustrated for a simple case of 2D rectangular reciprocal lattice. There here you can see, as I was discussing, so here there is one point. Let me. So here there is one point, another point here, another point here, another point here, point here, point here, point here, point here, point here. So between these 2 points, this is the perpendicular bisector they are telling. Between these 2 points, this is the perpendicular bisector. Between these 2 points, this is the perpendicular bisector. Between these 2 points, this is the perpendicular bisector. Yes, of course, you can, if you take this and this, the perpendicular bisector will be somewhere here. It is assumed that this line is beyond this rectangle. That's why this rectangle is kind of the primitive cell in the reciprocal space. And this is the first Brillouin zone. Okay. So how exactly it is? How exactly it is kind of obtained? So join the nearest neighboring reciprocal lattice points. Join the nearest neighboring reciprocal lattice points with the origin. Draw perpendicular bisectors. Draw perpendicular bisectors. Perpendicular bisectors, once you draw, the area enclosed by these bisectors, the area enclosed by these bisectors, PQRS, is the first Brillouin zone. Is the first Brillouin zone. Okay. Is this part clear to everybody?
Yes, sir.
Okay. Next, we move over to X-ray diffraction by a crystal. X-ray diffraction by a crystal. So, uh, in the beginning, we have discussed why X-rays are needed. Why X-rays are needed. So that is kind of explained over here also. To understand, sorry, to understand how X-ray diffraction by crystals provide information about their band structure, it is important to understand how they interact with the crystal. That is very much true. To understand the X-ray diffraction by crystals. So crystals diffract X-rays, and that diffraction provides information about the internal structure of the crystal. So how exactly the diffraction of X-rays is providing information or structural information about the crystal? It is important to understand how they interact with the crystal, how X-rays interact with the crystal. So if we understand how the X-rays interact with the crystal, then only we can understand how they are giving the information about the crystal or structure of the crystal. The first aspect we must appreciate is that for achieving diffraction, any probe, electromagnetic or otherwise, must have wavelength of the order of interatomic distance. This is most important line which is mentioned over here. Okay. So the first aspect we must appreciate is for achieving diffraction in any probe electromagnetic or otherwise must have wavelength must have wavelength of the order of the interatomic distances, which is 10 to the power minus 10 meter. For X-rays satisfy this condition, their energy must be E is equal to h nu, right? E is equal to h nu, where nu is equal to c by lambda. That's why it is E is equal to hc by lambda. If you substitute the value of h, which is 6.62 into 10 to the minus 34 joule second, c 3 into 10 to the power 8 meter per second, and lambda. What should be lambda? Lambda is 10 to the power minus 10 meter. 10 to the power minus 10 meter. Now, this 1.6 into 10 to the power minus 19 joule electron volt inverse. This is a conversion factor. This is a conversion factor. Let me write down conversion factor for going from joule to electron volt. From joule to electron volt, because here the energy is expressed in terms of electron volt. So if you kind of calculate it, you will find 12.4 into 10 to the power 3 electron volt. 12.4 into 10 to the power 3 electron volt. Okay. Now that X-ray of a few kilo electron volt. And the 3 electron volt is kilo electron volt. So X-rays of few kilo electron volt are required to probe microscopic structure of the solid using diffraction phenomena. You have so the sake of completeness, you can write X-rays are produced by sudden deceleration of electrons in metals as well as by excitation of core electrons in atoms by metallic target. Characteristics of X-rays energy is a few kiloelectron volt. X-rays are electromagnetic waves having 1 angstrom wavelength and are suitable for studying crystal structure. So this part is kind of explaining you why X-rays should be used to determine the crystal structure. Why X-rays? Why not visible light? Why not UV light? Why not infrared light? Why not radio waves? Why only X-rays are used for determination of crystal structure? So to understand that, the first aspect we must appreciate is that for any kind of diffraction effects to take place, that the wavelength of the probing light, which here in this case is X-ray, wavelength of the probing light should be of the order of the interatomic distance, should be of the order of the or the size of the object. Diffraction କେତେବେଳେ ହୁଏ? Diffraction ସେତିକି ବେଳେ ହୁଏ ଯେତେବେଳେ incident light ର wavelength ଟା ଯୋଉ ଅବଜେକ୍ଟ ତାକୁ ଡାଇଫ୍ରାକ୍ଟ କରିବ ତାର ସାଇଜ ସହିତ କମ୍ପାରେବଲ ହୁଏ, ସମାନ ହୁଏନି, କମ୍ପାରେବଲ ହୁଏ। ଗୋଟେ 1 angstrom ଅଛି, ଗୋଟେ 1.2 angstrom ହେଲା, ତାହେଲେ ସେଇ କେସରେ ଡାଇଫ୍ରାକ୍ସନ ହବ। କିନ୍ତୁ ଗୋଟେ 1 angstrom ଅଛି, ଗୋଟେ 100 angstrom ହେଲା ବା 1000 angstrom ହେଲା, ତାହେଲେ ସେଇ କେସରେ ଡାଇଫ୍ରାକ୍ସନ ଇଫେକ୍ଟ ଟା ଆମେ ଦେଖିପାରିବା ନାହିଁ। ଇଟ ୱିଲ୍ ବି ଭେରି ମିନିମାଇଜଡ। ଓକେ। ଆଉ ଏନର୍ଜି କେତେ ହେବା ଦରକାର? ଏନର୍ଜି ଇଜ ଇକ୍ୱାଲ ଟୁ h nu hc by lambda, and we found it is 12.4 kilo electron volt. 12.4 kilo electron volt. And it is kind of mentioned also here. The X-rays, how X-rays are produced? X-rays are produced by sudden deceleration of electron. Deceleration of electrons, opposite of acceleration. Deceleration of electrons, as the electron decelerates, it will release energy. It will release energy. And this energy falls in the range of X-rays. Yeah. Or how exactly X-rays can be produced? If you hit a metallic target with high energetic atoms, and that atom kind of knocks out, or particle kind of high energetic particle knocks out one of the core electron. If you knock out one of the core electron, then also X-rays will be produced. This is how in the laboratory X-rays are produced, and characteristic X-ray energies are few kilo electron volts only. Few. So X-ray ର जो energy ଆମେ metal target को hit କରିକି ପାଉଛେ, copper target को hit କରିକି ବାହାର କରାଯାଏ, ସେଥିପାଇଁ ସେଟାକୁ copper K alpha କୁହନ୍ତି। ବହୁତ ଜାଗାରେ ବହୁତ case ରେ ତମେ ଦେଖିବ, sorry, copper K alpha line. Copper K alpha line. This is a typical X-rays being used for probing of crystals. Okay. So what exactly that? So we bombard the copper target with high energetic particles, and that produces that knocks out one of the K electrons of copper, and that's how it emits energy which is in the range of X-rays. Is it clear?
Yes, sir.
Okay. Next, we move over to Bragg formulation or Bragg diffraction. What is Bragg diffraction? It is one kind of diffraction only. Diffraction phenomenon that you have studied in optics, that is diffraction only. But here, the object is a crystal. And what happens in a crystal? Uh, optics समझते पढ़ी सारिଛ ना optics पेपर ନା ଏଇ ସେମିଷ୍ଟରରେ ପଢା ହଉଛି?
A semester, this semester only it is there.
Okay, okay,
Not,
okay.
not,
So
not.
you can probably go through the material then on diffraction theory. Okay. So there you will see there is one topic called plane diffraction grating. Plane diffraction grating. Okay. Let me write it down. Okay. ଏଇଟା optics ରୁ ଟିକେ ଦେଖିବ for better understanding of this concept. All right. So it has been observed experimentally that the X-ray diffraction patterns of crystalline materials exhibit sharp spots. To explain these results, W.L. Bragg put forward a model which is resulted into the condition of diffraction in a very simple way. He proposed the crystals may be imagined to consist of parallel atomic planes. So this is one of the major. So he proposed that the crystals may be imagined. The crystals may be imagined to consist of parallel atomic planes. Parallel atomic planes, similar to stack of reflecting glass plates, similar to stack of reflecting glass plates. According to him, when the crystal is irradiated with X-rays, electrons in individual atoms scatter them elastically. So when X-rays are incidenting on the material, on the crystal, the electrons in individual atoms scatter them elastically, so that regular structure of atoms act as 3D grating. So here it is telling you the word grating. Okay, as you can see, grating. So this is kind of plane diffraction grating. That's why I told it is important that you go through the theory of plane diffraction grating, diffraction by plane diffraction grating in optics. All right. Now, waves or X-rays scattered from different atoms interact with each other constructively in some directions and destructively in others. So that means there is interference of these diffracted rays. When detected in X-ray film, the pattern is characterized by particular crystal structure. So what happens? Let me reiterate that crystal can be imagined to consist of parallel atomic planes. And when X-rays falls on these planes, so the planes act like a plane diffraction grating. And like grating diffracts incident rays, these crystal planes also diffract or scatter incident X-rays. And these reflected or scattered X-rays they interfere constructively and destructively to give an interference pattern, which is nothing but a signature of the crystal structure. As we have already discussed in we discussed in case of indices, isn't it? That if let's say if we have atoms or bases like this, then we can draw lines or planes, and these planes are characterized by H, K, and L. So the HKL value for this set of planes is quite different from this set of planes, and quite different from this set of planes, and quite different from this set of planes, isn't it? Huh? So So the figure shows 2D representation of a crystal structure to illustrate some of the many possible planes that could reflect X-rays. Isn't it? Let us now come to the mathematics part. Okay. Yeah, it is telling you to explain sharp spots in diffraction pattern. Bragg considered specular reflection by atoms in one plane and reflected waves from the successive. This is important to the specular reflections successive parallel planes separated through a distance to interfere constructively. The path difference between the two specular reflected waves in X-rays is AB plus BC. କେମିତି ହଉଛି କେମିତି ହଉଛି let us try to understand from this figure over here. So these are the incident X-rays, isn't it? So this X-ray line or X-ray kind of hits this particular plane and gets reflected from here. So incident angle over here. This one is, let me draw it small. Yeah. So this angle is incident angle, and this angle, whatever is drawn over here, huh? So incident angle is equal to the theta is the incident angle. Theta is not incident angle; it is the grazing angle. It's the angle it makes with the crystal. So this is theta. If I call this to be alpha, then alpha plus theta is equal to 90 degrees. So you can imagine. So incident angle is equal to reflected angle. That is why this is theta. This will also be equal to theta. Right? Now, the another X-ray, hmm, which is coming like this, gets reflected from the next plane and gets reflected like this. Now, these two rays, this one and this one, they are parallel. So, and they are also, since this interaction is elastic means it does not lose any energy. Elastic means the X-ray does not lose any energy while interacting with the crystal. Energy loss, if there is no energy loss, elastic scattering, then possibly they will interfere. Now, if they interfere, what is the path difference? That's what it is telling in this part. The so this part up to this normal, the same path up to this normal, it is same path. So it is only this part and this part. This is the path difference. So AB plus BC. If you just use simple geometry, AB plus BC would be d sine theta. D, what is D? D is the separation between this plane and this plane. So if this is D, this is theta. So you can, if I zoom it again, let me draw. Yeah. If this angle is theta, if this angle is theta, then yeah, and this is a normal. This is a normal for 90 degree. Let me draw on my board. Then maybe it will be more clear. Yeah, over here. So let's say I have two planes like this, and I have a normal. Hmm. So what happens? I have one ray coming like this and gets reflected. Another ray, parallel ray, is coming like this. My drawings are not that good. Reflected. So if I drop a normal over here, hmm, and I will also drop a normal over here. If this angle is theta, so this total angle is 90 degree. So this part will be this part would be 90 minus theta, right? Now, if this is 90 minus theta, so then this part would be theta because this angle is 90 degree, right? So this is theta and this angle is also theta. But what is this? This part, this is D. If this is D, this is theta. What about this one? What about this one? D cos theta, right? Sorry, D sin theta, right? So this part would be D sin theta. Similarly, this part would be D sin theta. So the total path difference would be D sin theta plus D sin theta, which will be equal to 2D sin theta. And for constructive interference, what will happen? Path difference should be equal to n lambda. So that is why 2D sin theta is equal to n lambda. Okay. If we come back to this diagram again, yeah. So 2D sin theta is equal to n lambda, where n is equal to 1, 2, 3, 4. This condition is basically called your Bragg condition. This condition basically called your Bragg condition. So so for different, it will not happen. This constructive interference will not happen for all theta. Only for certain theta, only for particular theta, it will have this constructive interference. And because of that, you will see only, let's say, 70 degree, here maybe around 64 degree, or maybe here around 56 degree, maybe 48 degree. You have this interference patterns or interference centers where the energy is kind of increasing. Here also energy kind of increasing. In other cases, there is no energy or no light. So these are nothing but so that's why I told. I mean, these are similar. These are kind of comparable to the diffraction pattern you get in case of a plain diffraction grating. But here, instead of just one grating, there are different gratings in different directions. There are different gratings in different directions. Okay. So it is telling, note that the angle of incidence of X-ray in X-ray crystallography is measured from the plane of reflection rather than from the normal to the plane. It is important, theta. The angle of incidence in X-ray diffraction or X-ray crystallography is measured from the plane of reflection rather than from the normal to the plane, as in classical optics. All right. Since sine theta is less than maximum value of sine theta is 1, so sine theta is less than equal to 1. You will note that for diffraction to be observed, we must have lambda less than equal to 2D. Lambda less than equal to 2D. What is D? D is the separation, interplanar separation. The separation between two planes in a crystal. And separation between two planes in a crystal is of the order of angstrom only. So lambda has to be of the order or should be less than 2 angstrom. Lambda should be less than 2 angstrom. So that's why the condition that only X-rays can only probe the crystal structure. Okay, is it clear? Bragg's law, is it clear?
Yes, sir.
Bragg's law to बुझिएला ना नहीं?
Yes, sir.
Okay. So at this point, I'll take 5-10 minutes break and then we'll start with Lau formation, which is basically similar to Bragg's law, but mathematically how we can get from reciprocal lattice space. Okay, we'll start after the break. Okay, should we start again? So let's start with love formulation, something called structure factor. So what is it? So according to love, the diffracted beam arises due to interference of X-ray scattered by all atoms in a crystal. So what is the origin of this diffracted beam? The law says that the diffracted beam arises due to the interference of X-rays scattered from all the atoms in a crystal lattice. Alright. While adding the contribution of these scattered waves, we have to consider their phases also. While adding the contribution of these scattered waves, we'll have to consider their phases. Okay, you will appreciate here that the difference in phases arises because waves travel different distance due to shaping between individual scattered atoms. What happens? Phases, why there is a phase difference? Phases arises because waves travel different distances due to spacing between individual scatterers or atoms. Okay. So here we shall discuss the diffraction of X-rays in a more general way by first considering the scattering of waves from a single atom. First, considering the scattering of waves from a single atom, and then collective effect of all lattice sites in a crystal to obtain the condition of diffraction maximum. So what exactly it is telling you? That the diffracted beam arises due to interference of X-rays scattered by atoms in a crystal. While adding the contribution of these scattered waves, you have to consider their phase differences or their phases. Why there should be, why the incident or the scattered lights, incident lights should have, sorry, scattered lights should have different phases? Because phases arises because waves travel different distance due to spacing between the individual scattered atoms. So here first we will consider the scattering of wave from a single atom. Scattering of wave from a single atom, and then the collectively what happens when light gets scattered by all the atoms. So scattering of an atom, which is basically called atomic scattering factor, scattering of an atom. We know that in an atom, electrons surround the nucleus. When these electrons are subjected to monochromatic beam of X-ray, they gain energy by subsequently lose it by emitting radiation in all directions, giving rise to spherical wavefront. You are familiar with the concept of spherical wavefront from your optics class. Eh? Also, you know that the plane electromagnetic wave may be represented mathematically by e to the power I k dot r minus omega t, where k0 is the incident wave vector. Where u, the incident X-ray can mathematically represented as incident X-ray can mathematically be represented as u is equal to a e to the power I k dot r I kx minus omega t. So instead of kx, since this is three-dimensional, it will be I k vector dot r vector minus omega t. K0 representing that it is a incident wave. And A, where A is the amplitude of the wave, A is the amplitude of the wave, and K0 is the wave vector. K0 is the wave vector where K0 is equal to 2 pi by lambda. And omega is the angular frequency. When the wave is incident on a single electron, when the wave is incident on a single electron, the scattered wave is spherical and the amplitude decreases with distance. This is important. When the wave incident on a single electron, the scattered wave is spherical and the amplitude decreases with the distance. So mathematically, how exactly you will write? Mathematically, this is kind of incident. This upper one, the upper one, this is incident. Incident. This is scattered. Okay. So the scattered wave can be written u prime is equal to Fe into A by D e to the power I k dot d minus omega t. Where Fe, what is Fe? Fe is the scattering length of the electron representing the fraction of radiation scattered by electron. We need to understand this part. What is Fe? Fe is the scattering length of the electron. Scattering length of the electron. What does it represent? It represents the fraction of radiation scattered by the electron. This is telling that if you are shining crystal with X-rays, not all the X-rays are falling on one electron. A part of it, only a fraction of it, is kind of scattered by that electron. So it is representing the fraction of radiation scattered by the electron. D, capital D is the radial distance between the electron and the point of observation. Capital D is the distance, radial distance between the electron and the point of observation, where the detector or the photographic film is placed. And K is the wave number scattered of the scattered wave instead of K naught, here it is K. For elastic scattering, K has the same magnitude as K0. For elastic scattering, K has the same magnitude as K0. Okay. In case the incident wave acts on two electrons, if the incident wave acts on two electrons, what will happen? So first there will be, let me zoom it. There will be this Fe part will be there. There is the fraction A by D. This is same as this A by D. And there are two waves. One is e to the power ikd, and another one will be e to the power ikd plus delta. This delta is the phase. This delta is the phase. And it is already explained. Like why should there be phase? It has already told you that here. Huh? But in phases arises because waves travel different distances due to spacing between the individual scatterers. So that's why what we will have? We will have u prime is equal to Fe A by D e to the power ik dot D plus e to the power ik dot D plus delta. Okay. So what will happen if we add these two? If we add these two, what exactly will happen? We'll see. Where delta is the phase difference between the two scattered waves. Note that the time factor has not been mentioned in the above equation, but its presence is implied in delta. ओमेगा टी कुआडे गला ओमेगा टी टा जे डेल्टा भितर अछि alright. Now if we see what is delta 1, we try to look at this diagram. What is delta 1 and what is delta 2? What is delta 1 and what is delta 2? So delta 1 is equal to BC. Delta 1 is equal to BC, and delta 2, this is, I guess all of you have gone through in optics this Huygens reconstruction or Huygens principle. ସମସ୍ତେ ପଢିଛ Huygens principle optics रे? ସମସ୍ତେ Huygens principle ପଢିଛ ନା ନାହିଁ? ୱେବ ଫ୍ରଣ୍ଟ କଥା ଯୋଉଟା ରିଫ୍ଲେକ୍ସନ ରିଫ୍ରାକ୍ସନ Huygens principle. Yes or no? এইটা ବି ଟିକେ ତାହେଲେ ପଢିବ କାରଣ ଅପଟିକ୍ସ ଟା ଏଠି ଟିକେ ଦରକାର। ସରି। Alright. So what exactly is happening? First case, so one X-ray comes over here, hits this. So there is one electron here. So it will act as secondary source and it will create spherical wavefronts like this. It will create spherical wavefronts like this. All right. It will create spherical wavefronts. Now, similarly, the second one will come. The second one will come over here, and it will also create these spherical wavefronts. All right. Hmm? Just then after reflection, in after reflection uh, from the first one, it is kind of incident, and this is kind of reflected. So this is kind of incident. This is kind of reflected. So the path difference delta 1, sorry, the path difference delta 1 between this one and the second one, S1 and S0. Sorry, S0 and so this, let me call it 1 and this call it 2. Between 1 and 2. 1 and 2, the path difference would be BC. So that is what it is written. D delta 1 is equal to BC, which is R cos theta 1. R cos theta 1. Or R dot S naught. R dot S naught. Or S prime. Sorry. S cap. Uh, what is S cap? Direction. This direction. So delta 2 is the path difference between the two waves scattered by the electrons between 3 between 3 and 4. That is basically this is between 1 and 2. This is between 3 and 4. Delta 2 will be equal to AD, the perpendicular distance AD, huh, from here to here. So AD is equal to R cos theta 2, which is R dot S. And if we try to see what is the total difference, that will delta will be equal to delta 2 minus delta 1, which will be equal to RS minus S cap minus S0 cap. If K0 and K1, sorry, K0 and K are wave vectors, so the incident and the scattered wave, so we can write K delta K is equal to K minus K0. Delta K is equal to K minus K0, 2 pi by lambda S cap minus S naught. But from here we know what is S minus S naught. So if we substitute that, then we will get delta k, where delta k is called the scattering vector. It's called the scattering vector. So delta k will be equal to 2k sine theta. 2k sine theta. All right. And the phase difference between the reflected wave can now be written as 2 pi times delta, which is basically equal to r dot delta k. R dot delta k. All right. So then u prime will be equal to Fe A by D e to the power I k dot D. If we take common, then it will be 1 plus e to the power I r dot delta k, because delta your phase difference is equal to r dot delta k, r dot delta k. Earlier it was, if you look at here, if you look at this expression, it was I k d plus delta. That means e to the power I k d dot e to the power I delta. So from instead of delta, what will write? R dot delta k. So that's why this expression. Okay. Now if we add another, if the origin is taken as arbitrary point rather than at one of the electrons, the expression for resultant scattering wave can be written as, instead of 1 plus r e to the power I r dot delta k, it will be having e to the power I r1 dot delta k plus e to the power I r2 dot delta k. What is the difference? Here, the origin is taken as an arbitrary point rather than one of the electrons. All right. So then, what will happen for a collective effort, for a collective result? We have to add all these kind of factors. We have to add all factors which are like this kind of factors. So that is what it has done. So u prime will be equal to f naught a by d e to the power I k d summation e to the power I rn dot delta k, where n runs from 1 to capital N, total number of electrons, such electrons. Okay. So this can be written as, so comparing equation 11 and 211 and 233. 211, what was 211? Coming to 211, okay, just to show you. DHKL is equal to OH cos phi, 211. Hmm? So comparing 211 and equation 33, we can define total scattering length. Total scattering length F is equal to F naught summation e to the power I Rn dot delta k. So that is represented as F. That is represented as F. So then 1 minus, sorry, U prime would be equal to F A by D e to the power I k d. All right. So this is basically your, okay. So instead of, if it is a continuous one, you can see this instead of summation, it will go to this integration. It will go to this integration. So what is now defined, the parameter called atomic scattering factor. Atomic scattering factor. So Fa is a ratio of radiation amplitude scattered by the actual electron distribution. Fa is the ratio of radiation amplitude scattered by the actual electron distribution in an atom to that of the scattered by a single electron. So scattered by an actual electron distribution to that of scattered by a single electron. So here it is a distribution of electrons. Distribution of electrons versus here it is single. All right. And this diagram is basically, this is a sinc function, sin x by x kind of term. So here you can see sin r delta k by r delta k. So this is more like sin theta by theta form. eh, Sinc function. eh. All right. Is this part clear to everybody? Is this part clear to everybody? Yes or no? Am I audible?
Yes, sir. Audible.
Okay. All right. So this is bit of mathematics. I can understand. This is bit of mathematics. So here you have to kind of little bit practice for the from exam point of view. Here you have to practice a little bit before going to the exam. Uh, but I think as I have mentioned, if you try to compare with your optics paper, so this is also basic, not MSc optics. This is more BSc optics actually. Plane diffraction grating, Huygens principle. That if you kind of revise, then it is very easy to understand this part of X-ray diffraction by now. Okay. Let me come to the book. Book also you can try to understand a little bit. So it will be help you. Yeah, so Fourier analysis of the basis and so yeah. So this is your 2D sine theta is equal to n lambda. Hmm. 2D sine theta is equal to n lambda here. Huh? And so here the approach is basically similar, but here it has taken the electron distribution as the starting point. Yeah, this is extra material. Anybody interested can read this. Okay. But other than that, your study material is very well written. You can simply follow that one. That's fine. Okay. So maybe I'll take a couple of minutes break and then I'll start with the next part, which is geometrical structure factor or the from atomic form factor. What we have discussed earlier was form factor. Next will be the scattering from a crystal. So lattice or geometric structure factor. We'll try to understand what is geometric structure factor. Okay. Just take a couple of minutes break, try to understand what we have already discussed, and then we'll move over to the next part, which is geometric structure factor. Okay. Okay, we may start again. Scattering from a crystal. There is a typo over here. Scattering from a crystal, not from a crystal. Lattice and geometric structure factors. Says that from the above discussion, you know that the intensity of an X-ray beam diffracted by an atom depends on its atomic scattering factor. So what is atomic scattering factor? If I try to explain, ମାନେ ଯଦି ବୁଝେଇବା ପାଇଁ ଆମେ ଚେଷ୍ଟା କରିବା ଯେ atomic scattering factor ଟା କଣ? ଯଦି ଏକ୍ସରେ ପଡିଲା ଗୋଟେ ଏଟମ ଉପରେ ଏଟମ ର ଇଲେକ୍ଟ୍ରନ ଗୁଡା ହିଁ ଇଣ୍ଟରାକ୍ଟ କରିବେ ଆଉ କେତେ କେତେ incident beam scatter ହବ, how much fraction of or how much of the incident beam is scattered by an atom. That is basically your atomic scattering factor. So that is what it is telling you, that the intensity of X-ray beam diffracted by an atom depends on its atomic scattering factor. The total scattering from a crystal, the there is a typo. The total scattering from a crystal will depend on the atoms constituting the crystal and their arrangements in the crystal. So, the total scattering from the crystal will depend on the atoms constituting the crystal and their arrangements in the crystal, that is the number, the type, and the distribution of atoms within the unit cell. That is very much important. So here it is not only just atoms, it is not only just atoms, but it is how many are the number, the type means number means we are considering how many, whether it is FCC, BCC, base center, simple cubic, primitive, and then type. What are the types of the basis atoms or basis molecules, and the distribution of atoms within the unit cell. Distribution of atoms within the unit cell. Moreover, the scattered waves originating from different atoms of a unit cell may or may not be in phase with each other. This is very much important. What it is telling, that the scattered waves originating from different atoms of a unit cell may or may not be in phase with each other. It is therefore important to know the effect of various atoms present in a unit cell on the total scattering amplitude of a particular direction. So that is to understand that, to this end, by analogy with atomic case, we define a parameter called crystal scattering factor. Like atomic scattering factor, here it is defined as crystal scattering factor. Hmm. The crystal scattering factor, huh, FC, huh, FC is equal to summation over P e to the power I RP dot delta K. When sum extends over all electrons in the crystal, as discussed before, this may be considered as to be made up of two parts. There are two parts. What are that? The first sum over all electrons in an atom, the sum over all electrons in an atom, and define the atomic scattering factor FAY for the yth atom, and then sum over all the atoms in the crystal. First कौन करिबा? First sum over all electrons. आगो गोटे एटम रो सब इलेक्ट्रॉन गोटे इलेक्ट्रॉन केते स्कैटर करिवो, that is atomic scattering, that is kind of ସେଇ amplitude ଟା ଆମେ ଜାଣିଛୁ। ତେଣୁ ଗୋଟେ ଏଟମ ର ସବୁ ଗୁଡା ଇଲେକ୍ଟ୍ରନ ସ୍କାଟର କଲେ କେତେ ହବ ସେଇଟା ଫାଷ୍ଟ ବାହାର କରିବା, ତାପରେ କଣ କରିବା ସବୁଗୁଡା ଆଟମକୁ ଆମେ ସବୁଗୁଡା ଆଟମ ର କଣ୍ଟ୍ରିବ୍ୟୁସନ କୁ ଆମେ ଆଡ୍ କରିଦବା। ସୋ ସେଇ କଥା ସେ କହୁଛି this is done in two parts. First we sum over all electrons in an atom and define the atomic scattering factor for the yth atom, and then sum over all the atoms in the crystal lattice. Okay, so Fc will be equal to summation over P e to the power I R y. So you can see R y, hmm, R y delta k. Summation over P R y delta k, where R y is the position vector of the yth atom. R y is the position vector of the yth atom. All right. Now to simplify this equation over here, to simplify this equation, eh, refer to figure 2.20. This one, this figure. This is what it is telling. We already discussed. It's shown that a 2D non-Bravais lattice with bases consisting of two types of atoms A and B, depicted as cross and circle respectively. The unit cell in this lattice consists of one atom. So here in this case, there is only one atom per unit cell, which might not be true for all cases. Atom each of type A and B, let the origin of the lattice is at O, while O prime is the reference point on the mth unit cell. Hmm. So if we do this kind of thing, then what we will get? This is so Ry will be equal to RCM plus alpha J. What is RCM and what is alpha J? Now it is clear that we can express the sorry. Okay. All right. So RCM is defines the position of the unit cell with respect to O, and alpha 1 and alpha 2 denote the position vectors of A and B respectively with respect to O prime. ତାମାନେ କଣ କରୁଛେ ଆମେ ଏଇ କେସରେ କଣ କରୁଛେ ତାକୁ ବୁଝିବା ପାଇଁ ହେଲେ ଆଗ ଆମେ କଣ କରୁଛେ ଗୋଟେ ୟୁନିଟ ସେଲ କୁ ଗୋଟେ ୟୁନିଟ ହିସାବରେ ତାକୁ ନେଇକି ଆଗ ଡାଇନାମିକ୍ସ ରେ ବାହାର କରିଦଉଛେ, ତାପରେ ୱିଦିନ ୟୁନିଟ ସେଲ କୋଉ ଭଳିଆ ସ୍କାଟରିଂ ହଉଛି ସେଇ କଥା ଚିନ୍ତା କରୁଛେ। ଗୋଟେ କ୍ରିଷ୍ଟାଲ ର ଟୋଟାଲ ସ୍କାଟରିଂ ଟା ଜାଣିବା ପାଇଁ ହେଲେ କଣ କରିବା, ଆମେ କହିବା ଯେ ନାଇଁ ଗୋଟେ ୟୁନିଟ ସେଲ କୋଉ ଭଳିଆ ସ୍କାଟରିଂ କରୁଛି ସେଇ କଥା ଆଗ ବୁଝିବା, ତାପରେ ମଲ୍ଟିପ୍ଲାଏ କରିବା ତାକୁ କାହା ସାଙ୍ଗରେ, ଯେ ଇଚ୍ ୟୁନିଟ ସେଲ ଭିତରେ ପୁଣି ଯୋଉ ଏଟମ୍ସ ଆଉ ଇଲେକ୍ଟ୍ରନ୍ସ ଗୁଡା ଅଛନ୍ତି ସେମାନେ କୋଉ ଭଳିଆ ସ୍କାଟରିଂ କରୁଛନ୍ତି। ଏ ଦିଟା ଫ୍ୟାକ୍ଟରକୁ ଯଦି ଆମେ ମଲ୍ଟିପ୍ଲାଏ କରିଦେବା ତାହେଲେ ଆମେ କଣ କଣ ଜାଣିବା, ଯେ ଆମେ କେତେ ଟୋଟାଲ ସ୍କାଟରିଂ ହଉଛି ସେ ପାର୍ଟଟା ଆମେ ଜାଣିପାରିବା। Now, coming back to the mathematics, if we substitute ry ଜାଗାରେ ଆମେ ଯୋଉ ry ଲେଖିଥିଲୁ ଏଠି ଫାଷ୍ଟ ଯୋଉ ଆମେ ry ଲେଖିଥିଲୁ ଏଠି we have written ry, right? So here this equation, if you ry ଟାକୁ ଆମେ substitute କରିବା, ଏଇଟାକୁ ଆମେ substitute କରିବା ଏଥିରେ, ତାହେଲେ କଣ ହବ? Then we will get this equation. Okay, double summation, because one summation over there, one summation over here over alpha. So rearranging, ଆମେ ଯଦି multiply factor ଏଇ factor ଟାକୁ ଏଠିକି ତାକୁ rearrange କରିବା e to the power i rcm into delta k, rcm into delta k, ଆଉ ଗୋଟେ alpha j into delta k, alpha j into delta k, ଏଇଭଳିଆ ଦିଟା part କଲେ can imagine. So capital F is represented as this one, f I j. This part is basically represented as capital F over here. And the second summation jota I part ta rahila, this part is basically S or SC over written over here. F is called geometrical structure factor, and S is called lattice structure factor. Geometrical structure factor और lattice structure factor कौन? Lattice structure factor माने total lattice point गुड़ाक हिसाब रे कोटा आसुଛି, geometry माने shape हिसाब को shape रे अछि, है ना? तो এই কথা সে কইছি, এটি লেখিছি বি সেই কথা যে note that F depends on the geometrical arrangement of atoms within the unit cell. Geometrical arrangement of atoms within the unit cell, whereas SC depends on the arrangement of cells within the lattice. তাহলে SC টা কোন? and जो কথা ମୁଁ କହୁଥିଲି multiply ହେବ, जो factor ଟା ମୁଁ ଯୋଉଟା କହୁଥିଲି ଦିଟା factor କୁ total ଟା ଆମେ ଜାଣିବା ପାଇଁ ହେଲା ଗୋଟେକୁ ଆଉ ଗୋଟେ ସାଙ୍ଗରେ multiply କରିବା, FC into SC. Okay, ଏ part ସମସ୍ତେ clear ହେଲା ନା ହେଲାନି? Yes, slightly mediocre level of mathematics. Mathematics ଟା କଲେ ଭଲ ଜବ ବୁଝି ହବ, ଗୋଟେ ବାଇ ଷ୍ଟେପ କଲେ ନିଜେ ଜାଣି ହବ, କିଛି ଅସୁବିଧା ନାହିଁ। I'll possibly leave it to you for self study of this part, so then to understand what exactly is happening. ये formula ମୁଁ କହିଦଉଛି from exam point of view ରୁ କେମିତି କୋଉଟା important. So this formula is quite important. What is it? এটা কোনটা? এটা হচ্ছে generalized form of geometric structure factor. Okay, generalized form of geometric structure factor. All right. simple cubic case रे कौन हबो? simple cubic case रे from unit 1 we recall, माने एई जो ब्रैकेट भितरे जोटा अछि सेटा inside the unit cell. structure factor कहछि परा, structure माने का ऊपर डिपेंड करबो, inside the unit cell structure को भले अछि, एई कथा सबले मन रखो। f टा होछि कोनटा एटी अब जो कथा से कहला, सेई पार्ट निहाती मन रखिबो। What is F? F is called geometrical structure factor, and SC is called the lattice structure factor. ତେଣୁ geometrical structure factor ଟା କାହାକୁ ଡିଲ୍ କରୁଛି? ଗୋଟେ ୟୁନିଟ ସେଲ୍ ଭିତରେ କୋଉ ଭଳିଆ ଆରେଞ୍ଜ ହେଇକି ସେ ରହିଛନ୍ତି। ଆଉ lattice structure factor ଟା କାହା ଉପରେ ଡିପେଣ୍ଡ କରୁଛି? ଟୋଟାଲ ଯୋଉ ୟୁନିଟ ସେଲ୍ ଗୁଡା କୋଉ ଭଳିଆ ଆରେଞ୍ଜ ହେଇକି ରହିଛନ୍ତି। यूनिट सेल गुड़ा को बड़े अरेंज ହେଇକି ରହିଛନ୍ତି ସେଟା ଲାଟିସ୍ ଷ୍ଟ୍ରକ୍ଚର ଫ୍ୟାକ୍ଟର ଆଉ ୱିଦିନ୍ ଏ ୟୁନିଟ୍ ସେଲ୍ ଏଟମ୍ସ ଗୁଡ଼ା କୋଉ ଭଳିଆ ଆରେଞ୍ଜ ହେଇକି ରହିଛନ୍ତି ସେଟା ହଉଛି ଜିଓମେଟ୍ରିକାଲ ଷ୍ଟ୍ରକ୍ଚର। ଏଇ ଯୋଉ ଫର୍ମୁଲା ଦେଇଛି ଏଥିରେ ଆମକୁ ବେସିକାଲି ଏଫ୍ ବାହାର କରିବା ପାଇଁ କହୁଛି ଏଣ୍ଡ ଏଫ୍ ୱିଲ୍ ଡିପେଣ୍ଡ ଅନ୍ ୟୁ ଜେ ଏଚ୍ ଭି ଜେ କେ ଡବ୍ଲ୍ୟୁ ଜେ ଏଲ୍ ହବ ଏଚ୍ କେ ଏଲ୍ ଆଇ ଦେଇ ଦେଇଛି ଏଟା ଏଲ୍ ହବ ପ୍ରିଣ୍ଟିଂ ମିଷ୍ଟେକ୍ ଏଚ୍ କେ HKL. It should be HKL. Okay. Correction करना पड़ेगी HKL. ତେଣୁ HKL ହେଲେ କହୁଛି ୟୁନିଟ୍ simple cubic ପାଇଁ ଆମେ ଯଦି ନବା consider simple cubic that the effective number of atoms in a unit cell of a simple cubic is 1 assuming that on this atom lies at the origin. So ଯଦି ସେଟା origin ରେ ରହିଲା ତାହେଲେ UJ0 BJ0 WJ0 0 0 0 ହେଲେ e to the power 0 is 1. So summation of her f a j summation of her j will be equal to some simple constant fa. So this is the simple cubic structure. So FHKL equal to atomic scattering factor. FHKL, so geometrical structure factor is equal to atomic scattering factor. Geometrical structure factor is equal to atomic scattering. Whereas in case of body centered cubic, what happens in case of a body centered cubic? Body centered cubic रे दीटा अछंती. There are two atoms in a body centered cubic. ताको जदि हमें इमेजिन करबा गोटे 0 0 0 रे अछि आ गोटे हाफ 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 रे अछि. 0 0 0 माने गोटे कॉर्नर. बॉडी सेंटर टा को बढिया. हेलो. We see the body center. Let us draw it. Okay. And then one over here. One over here means it is from all directions. It is at half half half. So the coordinates are 0 0 0. If the length side length is like 1, if the side length is 1, so this will be 0. uh, if this is 0 0, then this will also be 0 0 1 0 0. And this will be 1 1 0, and this will be 1 1 1. So this midpoint over here, that will be 1 by 2 1 by 2 1 by 2. So it is telling that uh, so each atom at the corner, each atom at the corner is shared by 8 unit cells. Hmm? Okay. So hence contribution is 1 8. Hence contribution is 1 by 8. Hence there are 8 such atoms at the corner. So contribution will be 8 into 1 by 8, which is equal to 1. So to visualize, we can say this is one atom, and in the middle there is another atom. So there are in total one at middle, half, half, half. Okay. So then we can say, so there are 1 plus 1, there are 2 atoms per unit cell. So these 2 atoms, we can imagine that one is at 0, 0, 0, another is at half, half, and half. You will say, what about the other ones? The other ones will be counted in other unit cells. So for this unit cell, we will consider one atom at 0, 0, 0, and one at half, half, half. Okay. If we take this concept, hmm, and we move over to here, so half, half, half. So if we substitute that, substitute what? Uj is equal to half, Vj is equal to half, and Wj is equal to half. And Uj is equal to 0, Bj is equal to 0, Wj. So if we substitute those values, you will see it will be FHKL will be equal to Fa, will be equal to Fa into 1 plus. First case is we substitute Uj is equal to 0, Vj equal to 0, Wj is equal to 0. So e to the power 0 is 1. So that's why this 1 is there. And then if we substitute half, 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 it will be 2 pi into half. So that is pi e to the power I pi h plus k plus l. Okay. So if h plus k plus l is equal to is an odd number, if h plus k plus l is equal to an odd number, so this will be equal to e to the power I pi into h plus k plus l will be equal to -1. So then it will be 0. And if it is even, if it is even, then what will happen? It will be equal to 2Fa. It will be equal to 2Fa. That's what it is telling you over here. All right. So similarly, you can also find out for FCC. And I'm not seeing that FCC. Where is it? Is that? No, where is that?
কভারে দে তো
Yeah.
গুনিয়া ঢুকিয়ে আছে
Yes,
ও চাপ বেরাতে না
I can show you in the book also. It is there. Just for reference, you can show you. Yeah, over here. So this is for structure factor for BCC lattice and structure factor for FCC lattice. For first, as we already have discussed, in one case it will be x1, y1, z1 will be equal to 0. Other one will be x1, z1, and x2, y2, and z2 will be equal to half. So this is like 0, 0, 0, and this is half, half, and half. Okay. For FCC, we have actually 4 atoms. You remember, we have actually 4 atoms. Let me clarify that a little bit. So if you draw it, hmm, so corners, at 8 corners. And then on each face, one over here, one over here, one over here, one over here, and one over here, and one over here. Okay. So uh, let me write down one part is each corner atom shared by 8 unit cells. So this implies contribution is equal to 1 by 8, but 8 such corner atoms. This implies total contribution is equal to 1 by 8 into 8 is equal to 1. Okay, this is one part. Second part is each face atom, face center, face atom is shared by 2, 2 unit cells. So this implies contribution is equal to 1 by 2. And there are 6 faces. So total contribution is equal to 6 into 1 by 2 is equal to 3. So total atoms, total atoms per unit cell is equal to 3 plus 1 is equal to 4. So this 4 you can say one is at 0, 0, 0. Other one is at half, half, 0. Other third one at half, 0, half. And another one you can say 0, half, half. Okay. This way you can define 4 units. And if you come back over here, you can see that's what it has told you 0, 0, 0, 0, half, 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 0, half, 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 0. If you substitute that, you will get 1 plus e to the power I pi v2 plus v3, v1 plus v3, and v1 plus v2. Hmm. And if all indices, this is important, if all indices are even integers, then s is equal to 4f. S is equal to 4f. Hmm. Similarly, if all indices are odd integers, but if only one of the integer is even and two of the exponents will odd, multiplying with this one, so s will vanish. If so, all are even, then s is equal to 4f. If all are odd, then s vanishes. If only one of the integer is odd, the same argument applies and s will vanish. So if all three are odd, then also a problem vanish. If one is odd, then also vanish. Thus, the FCC lattice, no reflection can occur for which the indices are partly even and partly odd. So, all even, then only it will be having S will be equal to 4. So, these conditions are actually, you can see BCC has different condition, FCC has different condition, simple cubic has different conditions. So conditions on what? Conditions on H, K, and L. So this is kind of telling you that not from all lattice planes will get diffraction intensities. Rather, depending on what kind of crystal we have, whether FCC, BCC, or simple cubic, or base centered, like that, we will get our X-ray diffraction patterns at different angle theta. So that is how we are getting a signature pattern from a crystal structure. Okay. Yeah. So I think I'll possibly stop it here. And next class, I will discuss little bit about the instrumental part of X-ray diffraction and how exactly the X-ray diffraction is being done. And then we'll move over to the next part, neutron scattering and electron diffraction. Okay. Any doubt, any questions you can ask me? Okay. If no more questions, then we possibly end the session here. Okay. No more questions, then we stop the session and see you on 27th.